Hi everyone. I'm going to be talking about P versus NP, which might not mean anything to you. So basically what this talk is going to be a short intro to computational complexity, and there's a lot of vocabulary, everything kind of builds on each other, so at the end of the talk we'll get to what P versus NP actually is. So the first thing we're going to define are decision problems. Decision problems are solved by an algorithm. They have a yes or no answer. They're decidable if the answer is yes or no, and they're undecidable if there's no answer, so it just never comes to a conclusion. Turing machines are a concept invented by Alan Turing in 1936 as a device used to talk about how we evaluate algorithms. So basically, like if you can imagine just like a box with a tape running through it, and the box can read what's on the tape, it can write something, or it can move the tape over. That's like all it is. It's just a very, very simple computer. So when you feed a Turing machine a problem, it is said to halt when it finds the answer. And then in that case, the problem is decidable because it decided on the answer. And if the Turing machine keeps going forever, then the problem is undecidable. Fun problem that Turing introduced was called the halting problem, which basically asked, can I create an algorithm that will tell me if another algorithm is going to halt? And the answer is no. So that's kind of like a meta problem. And the point of that, so like why do we have this stupid computer that doesn't do anything and that isn't real, and what's the point of the halting problem? Well, if we want to evaluate like how difficult a problem is to solve, if we use like IBM Watson, that doesn't really tell us very much about how difficult a problem is. But if we have just a really, really simple computer, then we can think of problems being solved by that simple computer instead. And the takeaway of the halting problem was kind of that there are unsolvable problems, which is nice and philosophical. So next, complexity classes. So within the world of decidable or solvable problems, we have like all these different classes of how difficult problems are. We're only going to talk about P and NP. So P. So P stands for polynomial time. These are problems that have a big O of n to the k, where k is a constant, so their big O is a polynomial. And these are kind of like, quote, easy problems. Polynomial time can take a long time, but it's really nothing compared to exponential time. And some examples of problems in polynomial time are just like multiplying things, sorting things, game of life. And these can all be decision problems too. If we say like, is 5 times 5 equal to 25? That's yes. Game of life, is this cell going to be alive in X life cycles? Yes or no? NP does not, NP does not stand for non-polynomial. It stands for non-deterministic polynomial time. And what deterministic means is kind of like every single stage of the algorithm has like a logical next step. It's the same every time. Non-deterministic, it eventually reaches a conclusion, but it has to like try out all of these different routes at every stage of computation. So it takes longer to find the answer, and it becomes really difficult when you have like a large input with a lot of possibilities. What's cool about NP, however, is that if you give me a solution, I can tell you if it's the right one in polynomial time. So, for example, with that Sudoku, it's very easy, you can check if a board is correct in polynomial time, but to actually solve a Sudoku board takes a while and is difficult. So therefore, it is in NP. Other NP problems include 2048, decryption, right? Like it's hard for me to come up with what your key is, but if you give me your key, I can tell you if you have access to my files. Classroom scheduling, protein folding. And there's also a problem called the traveling salesman problem, which I'm going to go into. It's not a typo. The noun has 2 L's. Okay. So the traveling salesman problem, I think we spoke about it in our class on algorithms. Given a list of cities and the distance between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the origin city? So a decision problem, like, can we find a route that's less than whatever distance? So brute force solution is O(n) factorial. It's pretty bad. Dynamic programming, O(n) squared 2 to the n, still pretty bad. And another NP problem is called the Hamiltonian Path problem. Given a graph, does a path exist where each vertex is visited exactly once? This sounds kind of a lot like the traveling salesman problem. Whoa. So yes, and this is an instance where you can, quote, reduce a problem to another problem. So that's called reduction, is when you kind of perform a bunch of calculations on a problem and then we have another problem. These two problems are part of a special class of NP problems called NP complete. They are in NP, and every problem in NP reduces to it. So essentially, if I find like an easy algorithm to compute an NP complete problem, I've just proven that I can compute any problem that's in NP in polynomial time. So you can kind of think of it as kind of this upper bound of difficulty. Problems in NP are not going to get any harder than problems that are NP complete. So just to wrap up, so we have NP, and then we have, which are verifiable algorithms, and then P, which are also solvable, and then our special NP complete problems. So fun times. There have been instances in the past where an algorithm was thought to just be an NP, but it turns out it's in P, and now we have like a bigger P. So the question remains, like, how big is P actually? Is P equal to NP or not? So that takes us to the P versus NP question, which says if P is the class of problems that are easy to find, NP are the class that are easy to verify, does it necessarily mean if a problem is easy to verify, does that mean by definition that there's also an algorithm to solve it? This is the most famous problem in computer science. It's one of the, quote, Millennium Problems, which are a list of problems by the Clay Mathematics Institute. If you can prove it either way, you will get $1 million. Number 6 has already been solved, so sorry about that. So let's go through what happens. Let's say P is not NP. Nothing really changes. Some problems might be in P, they might not be, and just a matter of figuring that out. If P equals NP, a lot changes very quickly. So first off, public key cryptography is out, like online security just falls apart. On a nicer note, everything will be able to be optimized, like exactly. And also how we solve problems would change. We'll probably spend less time coming up with new creative solutions to things and more time just trying to reduce every problem to a problem that we already have a solution to. This was a quote that I liked, kind of talking about this P equals NP world as this dream world where everything can be figured out by an algorithm. On a sadder note, if P equals NP, this professor, Scott Aronson, kind of described it as this sad situation where creativity isn't really valued anymore because everything can be quantified scientifically. That's basically it. So I hope that I've made some sense and that computational complexity is a really interesting field in theoretical computer science. There's also a really good YouTube video that I linked here, and I hope you win $1 million one day. And that's it.